This lecture is part of the undergraduate course Multivariable Calculus, and we would like to talk about parametric surfaces in space. If you remember, we parameterized curve for solving line integral. So let me give you a recall. For line integrals, which is the integral of a function ds or a vector field over a curve C, we solve this line integral by parameterizing the curve C. So we parameterize the curve C by a vector function. And the vector function that we're going to use has just one parameter, r of t, and has one parameter just because a curve has 1 degree of freedom. Basically, a curve is one-dimensional object, and a space curve is one-dimensional object that lives in three-dimensional space. So we just need one parameter to parameterize that, and since it lives in a space, it has 3 coordinates, a function of t as the first coordinate, y of t second coordinate, and z of t the third coordinate, and the parameter t is in an interval a and b. We use this parameterization to solve the line integral. Now we're going to talk about surface integrals. And for the surface integral, I'm gonna have the double integral over a surface S, and now as before, I need to parameterize S by a vector function. And the vector function that I'm gonna use now needs to have 2 parameters. Any 2 parameters would work. I'm gonna choose u and v, and I'm gonna have x of u and v as the first coordinate, y of u and v second coordinate, and z of u and v as the third coordinate. And any 2 parameters would work in here. But we need to pay attention that u and v, they live in a region D, where D is a region, a 2-dimensional region in UV plane. Okay, let me show it to you how it looks like. So as you see, I have a plane U and V, and then I have a region D. Any point U and V that I choose in the region D using the vector function R gets mapped to a point in the surface S. Okay, using this vector R of U and V, I show a point in a surface. That's how I parameterize the surface S that has basically 3 variables, right? Any surface, it looks like, for example, z equals to f of x and y, for example. It has 3 variables, but I use 2 variables, u and v, to parameterize that. Okay. So now we're gonna talk about some important parameterizations. Important parameterizations that we're going to use a lot in examples and homework problems. The first one is a graph of z equals to f of x and y. In this case, I'm gonna let x to be my first parameter, y to be my second parameter, and z a function of u and v. So in that case, r of u and v would be u, v, f of u and v, and u and v are in the domain of the function f. The second surface that we're gonna choose to parameterize would be sphere. Sphere of radius a, centered at the origin, has this equation: x squared plus y squared plus z squared equals to a squared. I'm going to parameterize that sphere. So let me show it to you, the graph of a sphere. This is a sphere of radius 5 in space. Okay, I'm going to parameterize this. Let me, instead of a, let me choose radius 5. Okay, to parameterize that, I'm going to use spherical coordinates. Okay, if you don't know what spherical coordinate is, we're going to explain that. So this is x-axis, y-axis, and then z-axis. Let me graph a sphere. Okay. So if I pick any point P in here with the coordinates x, y, and z, I'm going to show this length by rho. And if I have a sphere of radius 5, the length rho is equal to 5. Okay, so in this case it's equal to 5, or it could be equals to any radius a. And then I'm gonna show what z, x, and y are. I'm gonna use the angle between rho and the positive z-axis. So phi is the angle between rho and positive z-axis. Okay, as you see, phi could be between 0 and pi. Okay, because if the point is here, if the point P is here, then phi would be on this side, and it would be still between 0 and pi. So phi is between 0 and pi. Now I'm gonna look at this right triangle in here, and the length here in this right triangle would be z, and as you see, z would be, based on the right triangle in here, would be rho, which is 5 in here, rho cosine of phi. Good. Now I'm gonna project rho into the xy plane, and I'm gonna call it r. So I have a right triangle in here. In this case, r would be, as you see, r would be parallel to this side of the rectangle of the triangle in here. So r would be rho and then sine phi. Very good. Now if I connect r to the x-axis, the length here would be x, right? The x coordinate of the point P. But to address that, I'm going to consider the angle in here between r and the positive x-axis, and I'm going to call it theta. Theta would be the angle between rho, between r actually, between r and positive x-axis. And in that case, theta is between 0 and 2 pi. Okay, to make it round, to make the whole sphere, theta would be between 0 and 2 pi. And now that I have r, I have a right triangle in here, I can write x. So x here would be r, which is rho sine phi, and then it would be cosine of theta, and y would be exactly parallel to this after I kind of connect r in the right triangle to y. This length here would be y, which is parallel to that, and therefore y is r is rho sine phi, and then sine theta. Perfect. I graph, or basically I parameterize my surface with two parameters, phi and theta. Rho is fixed. Rho would be the radius, which is 5 or even a. So rho here would be 5, and as you see, I just have two parameters. Okay, so if I have the whole sphere equals to a squared, then the parameterization using two parameters, phi and theta, would be a sine phi cosine theta, a sine phi sine theta, and a cosine phi, where phi is between 0 and pi, and theta is between 0 and 2 pi. Okay, very good. That was for the sphere. For the next one, I'm gonna choose a plane. Let's choose a simple plane like 3x plus 5y plus 7z equals to 10. Okay, in that case, let x to be my first parameter, y to be my second parameter, and then z. To write z in terms of u and v, I need to isolate z. So it would be 10 minus 3x, x is u, minus 5y, y is v, divided by 7. Okay, and in that case, u and v are both in R. That's equation of a plane. Let me show it to you. A plane, oops. A plane is like this in a space, okay? And we parameterize that. The next one that we're gonna parameterize would be a cylinder. So I'm gonna parameterize a cylinder. Cylinder has equation like this: x squared plus y squared equals to a squared, and the third parameter is between c and d. Okay, for that, let me show the graph first. The cylinder, that was the plane. This is a cylinder. This is a cylinder of radius 5, as you see, and z is between -7 and 7. Okay. So to parameterize that, I'm going to use the fact that x and y lie on a circle. So if you remember polar coordinate, x could be a cosine theta. So a would be just the number, would be the radius. Y is a sine theta, and in that case, theta is between 0 and 2 pi to make it round, and z is free. Z doesn't depend on x and y, so z is free. Z could be my second parameter. So in that case, the cylinder has two parameters, theta and z, and it is a cosine theta. A is just a number, a sine theta, and z Z is in R, Z is free, or no, in the cylinder that I have here, Z is between A and B, between C and D, and theta is between 0 and 2 pi. Very good. That was the cylinder. Now, let's look at the last one, a cone. Equation of the cone is this: z squared equals to x squared plus y squared. Okay, let me show it to you, the graph of a cone. That was a cylinder. This is a cone. This is the cone z squared equals to x squared plus y squared. Okay, now if I have, for example, x squared plus z squared equals to y squared, then the cone lies on y squared. Y is changing, you see? The direction would be different than this one. Okay, so the pink one is z squared equals to square of the other two, and on this one it's y squared equals to that. Okay, now let me parameterize that. For parameterization, I have x, so because x and y are there on circle, x is something cosine theta, y is something sine theta, and then z is now depending on x and y, so it could be one of the parameters. Okay, I'm gonna call it u, and let's just, instead of u, let me just keep it z. And now, since x squared plus y squared is equal to z squared, z acts like the radius of that, so I have z in here as the radius. Okay, so in that case, theta is between 0 and 2 pi, and z is in r. So for that, r of theta and z would be equal to z cosine theta, z sine theta, and then z. And then theta is between 0 and 2 pi, z is in r. These are the parameters. Now compare the cylinder and the cone. As you see, this is the function of just one variable, theta. A is just a number. This is the function of just one variable, but in here I have a function of two variables. Z and theta are my variables or parameters in here. This is the function of two parameters or two variables. Okay, so that's the cylinder. This one is the cone. On the next video, we're going to solve some examples using the parameterizations that we discussed in here.